All right, so we've already briefly discussed some of the basic laws of linear perspective, and now we can get into some of the more practical applications of perspective, some of the reasons why it's very useful to know these laws of linear perspective, and the ways that they're going to apply to the kinds of drawings that we're going to be making. So I want to briefly start by covering some old ground again, and just briefly mentioning the basic ideas of linear perspective. And the first thing that we need to remember is that our horizon line is kind of the anchor of our scene. This is what all of our perspectival decisions are going to be made based on, because the horizon line represents our eye level in the scene. And so it's going to determine how objects appear to move up or down in relation to us. So I can imagine, for example, that if I place a box right on my eye level, I might only see the front of it, and as it goes above my eye level, maybe I begin to see a little of the bottom, and as it goes further and further above me, I begin to see more and more of this bottom space, and the same thing will happen going beneath my eye level. The further this box travels beneath my eye level, the more and more of this top of the box that's being exposed. So it's the very first thing to keep in mind is that the horizon line represents the height that my eyes are in relation to the object that I'm drawing. And we'll get to some practical places where I might find that eye level a little later on, but for now let's just leave it at that. So we have our horizon line. So let's place a new horizon line, and I'm going to draw a box. You can imagine that I'm drawing this from observation, maybe, that I have a box sitting in front of me, maybe in a little still life. And I've drawn this kind of just the way that we've been drawing, where I'm observing, I'm measuring angles, but there's still a certain amount of guesswork, especially when I start inserting other rectangles into the scene. So for example, maybe this box sits on a tabletop, and I might be curious how to make it really feel how this box sits on that tabletop and doesn't sink into it or float above it. And luckily, there are systems that people have constructed to describe the way that rectangular objects relate to each other in space. So again, if you watched the first video or were present for the first lecture, you'd know that linear perspective was designed to help us draw things like architecture. So rooms and buildings and cities, these kind of rectilinear forms where everything is at right angles. And what people discovered is that if I'm in a scene such like this, where I'm perfectly facing one side of this box, so this is me, this is a top-down view, I'm looking straight ahead, and the angle of my view is 90 degrees from one side of that box. So this side appears to be perfectly vertical, this side appears to be perfectly horizontal, the back appears to be perfectly horizontal, and the only lines that aren't perfectly vertical or horizontal are these diagonals. And the same thing is true of this tabletop, and we call these diagonals orthogonals in perspective. And so anyway, what people discovered is that these diagonal lines, even though they appear to converge to a kind of V, they close towards the back, I know that they are actually parallel. The sides of a square table are parallel to each other. And so what people figured out is that, well, if parallel sides moving back in space always appear like they're closing, then they should touch at some point. And that is true. They will touch at some point, visually. Obviously, the two sides of a table are never going to touch, but if it were infinitely long, if it were like a railroad track going off towards the horizon, it would appear to touch eventually. And they don't just touch anywhere. they always touch at my eye level, wherever my eye level is. So, for example, let's say I'm sitting down and drawing this scene. And so I'm going to erase my orthogonals and redraw them, because now I can just connect all of my orthogonals to that point, and my scene will be constructed for me such that the box appears to be sitting properly on this tabletop. As long as these objects are at right angles to each other, perpendicular to each other, so that this box is square, again, 90 degrees, with the angle of this table, then all these lines will be parallel, and so they're all going to recede to the same point. And we call that point the vanishing point. Because again, that's, if this object were infinitely long, that's the point where it would appear to disappear. And again, the key is that these lines will recede to the vanishing point no matter where, or it will recede to a vanishing point on the horizon at my eye level, wherever my eye level is. So let's do a little example where I'm going to keep these objects right where they are. And let's assume that now I've stood up. And so now my eye level has raised a little bit. My objects look a little different, but it still agrees with my eye level. Since my eyes have raised up, I should be seeing more of the top of my objects. And receding to my vanishing point makes that happen. So the first rule of linear perspective is that parallel lines converge away from the viewer, and they converge to a point that lies at our eye level, no matter where our eye level is in relation to a scene. So, this is, kind of interesting. And again, this will happen with any, just to, drive this point home, this will happen without talking too long, but this will happen no matter where I place an object in a scene. So I can put a box anywhere in my view, and as long as this front face is 90 degrees to my vision, all of its orthogonals will recede to the same vanishing point. So, very useful, but obviously there are some complications in that I may have instances in which I want to draw a box that is not 90 degrees to my vision. And I'll try and speed this up a little bit, because if you've already watched the first lecture, you've already heard all this. But obviously I can't, just put a point right behind this object and connect my lines to it, because they don't hook up with anything anymore. It doesn't make sense. And that's because what's actually happening is that instead of having one point, as soon as I leave one point perspective, which is when I'm 90 degrees to the face of an object, I create a second point. And it's no longer going to be in the center of my vision, but instead it's going to be to the left and to the right, and all of my orthogonals should hook up with these points. The problem with two-point perspective is that a lot of times we're going to want to crop our page such that these points are not actually on our page. We can't actually measure those lines. So the key thing to keep in mind is, and in this instance, for example, our horizon line isn't even on our page. The key thing to keep in mind is that sets of parallel lines, so for example, these three lines are parallel, have to touch, and they have to touch at our eye level. So I can't ever draw a box. For example, it does something like this, because these two lines won't ever touch. I have to construct my box such that I at least get the sense that these three lines will eventually touch somewhere off in the distance, and that will hopefully be around where my eye level is. Just as a brief recap, it is also possible to have a single object with more than two vanishing points. For example, let's say that I'm drawing a tall building. I'm placing my sides on the building. I might get the sense that, oh, that doesn't quite feel tall enough. It feels like like the point of a sword more than something that's kind of stretching up into the sky. And the reason for that is that when we get very large objects or something that we're very close to, the sides of the building, our verticals are actually no longer going to be vertical either. And instead, they're going to recede to a third point up in the sky. So this is a 3-point perspective system. We'll pretty much only see this in buildings or very large objects. But go back and watch the first video again if you need a refresher on that. So anyway, very brief refresher on some of the basic systems of linear perspective, but the essential idea being that our eye level represents the height of our eye off the ground in relation to the objects in our scene, and that parallel lines all recede to the horizon at a single point. So let's talk about a few instances in which the concepts of linear perspective might be very useful. And just as a small example, let's say that I wanted to draw a crowd, for example, a bunch of people standing in the horizon or standing in a scene. And for the sake of simplicity, I'm going to just kind of draw a very sort of simple cartoony person. But all right, I have a person drawn in my scene. And what I find is that my eye level sits at about their shoulders. That's around where my horizon is intersecting them. And I could just sort of, go through and continue placing people throughout the scene, but I might get the sense that, oh, something doesn't feel right here. These people don't feel like they're sitting on the ground, actually. It feels like they're rising up as they go back into the distance. That's because, since my eye level intersects this figure at the shoulders, assuming that all these people are roughly the same height, which people are pretty much in the same ballpark, even if there are differences in height, that means that all figures in my scene should also intersect the horizon at the shoulders. No matter how small they get, that will be the point that they hook up with the horizon in, and that will give the sense much more natural, with a much more natural feeling that they are actually, receding back into the horizon. And I could do this with any kind of object. So, for example, I've put my people sort of more neatly in a row than they would naturally be. But you might imagine that, for example, that might be very desirable for drawing something like a row of telephone poles. And that if I have an object like this that's in a line that's evenly spaced, my job is even easier because I also know that since the bottom of all these objects are in a line, I should be able to draw a line through the bottom of all these objects and reach a single point, because these objects, since they're in a line, they describe a plane. I can kind of imagine them as describing the side of a box, and I should be able to do the same thing with the tops. And so, for example, I realize that I've made many of these much too tall. And so I can come back, and there, that describes much more convincingly a set of objects receding back into space that are all equally sized. And this will happen with any evenly sized, evenly spaced object going back towards the horizon. Windows on the side of a building. When we're working in the hallway, it'll be lockers on the wall, doorways that are all the same height. We can draw a line from the top and the bottom to a point on the horizon, to our vanishing point, that will help us get all of the even height along the entire scene. So I have the heights of all my objects described, and I'm pretty happy with that. But I'm not too certain about the width, because right now I have these spaced pretty much equally to each other. And really what should be happening is that they should be getting closer together as they go back. They should get denser as they go back into space, because the distance between them is getting compressed, is getting foreshortened. And I could measure that, for example, but let's, probably should have just cleared all instead of undoing, but I could measure that with my pencil visually, but let's try something a little more complicated. So let's say that I'm drawing a row of lockers on the wall. I don't know why my program is freezing like that. I guess I'll just freehand this. I've begun to describe the top angle of my row of lockers, my bottom angle. Let's say maybe this is a locker, and I want to continue this grid of lockers. But I'm not certain how far apart to place these objects. Well, if I can get any two vertical lines in my scene, then I can find all of my other vertical lines. So for example, if I were drawing, again, the telephone poles, I would need two telephone poles in order to find the placement for the rest. Here, I only need these few lockers because the left side and the right side of each locker is shared, so this kind of represents two of my evenly spaced lines. And what I want to do next is I'm going to find the midpoint of my locker. And again, here I've kind of done this purposely so that the midpoint is very conveniently just defined by my horizon. But again, it's the literal midpoint wherever that is. So if my scene was more like this, my middle would be somewhere here. It's the literal middle here. I could even take a ruler and measure this on my page. So if I have two vertical lines and my middle, what I can do is draw a line from the top of my first object through the middle of my second object until that touches the horizon. Touches the angle that describes the bottom of my objects. And if I do that, that defines where my third object could go. And I can continue to do that indefinitely, from the top of one through the middle of the other. Oops, wrong layer. And that defines where my fourth object could go. And you can feel how these are evenly regressing back into space. And I can continue to do this forever. And I can even do this on any plane of my picture. So I could, for example, use this to find the distance between rows of tiles on a floor. I can make a very convincing floor tile. I can use this to describe the placement of lights going back in space in a ceiling, or rows of seats in an auditorium. Anything that's evenly spaced and that's roughly at right angles to each other is going to follow the laws of perspective and will follow this rule, which is a very useful thing to know. And this rule can also help us describe foreshortening. So I mentioned foreshortening earlier, and foreshortening is essentially the idea that if I take an object, so for example, let's say that I, have a bottle sitting on a table, and I tip it over such that it's lying on the ground, it appears to have gotten shorter. It no longer has the same vertical height that it used to. And our brains, because we have binocular vision, we know what this distance is. We can still read this at its original full height, and our brain wants to draw it equal to that original height, which of course is going to make it feel enlarged and flipped up in space because it shouldn't be equal to that original height. It should compress as it goes back into space. And linear perspective can help us calculate that compression. So, for example, let's say that I am working on a tabletop. So I have a still life on a tabletop in 1 point perspective. Excuse me. And I have gridded out this tabletop. Maybe it's on a checkered tablecloth or something. Maybe I'm just gridding this out to kind of help myself. And I'm using that from the top of one through the center of another to find where my back checker should be, and that's good enough for me. And let's say that I have an object that fills up. Let's change color so it's a little easier to see. I have a water bottle that's maybe 4 squares wide, and it's sitting on the table, perpendicular to my vision, right here. And I want to sit that back into space. Well, I can just count. Actually, I should probably finish. All right, so I realize I didn't give myself 4 rows of squares. All right, so I can count back 1, 2, 3, 4 squares and know that that's the space that that object should occupy. And now it's visually much shorter than it used to be, but I'm using this grid, which I've compressed back into space, to help automate some of the confusion around compressing an object. So another very useful kind of thing that I can use perspective for. A last thing that perspective is used for, but a very, very important thing, is that linear perspective is incredibly useful for helping us draw an ellipse. And an ellipse is essentially a circle that is sat back in space, the same way that we've been taking squares and flipping them down. Now, there are a few common problems that we run into with an ellipse. The first is that, just the same as it's relatively difficult to draw a circle that's kind of a perfect circle freehand, it's kind of hard to draw an ellipse that feels right. A lot of times we end up making it too pointy at the edges or too flat at the top and the bottom sides. It becomes too much like a rectangle, and really it should only reach its extremities, its widest and tallest points at 4 edges, the same way that a circle sort of is always curving away. It shouldn't reach those points too sharply or too flatly. Now with a circle, we can help ourselves a little bit. It's much easier to draw a perfect square than it is to draw a perfect circle. Now from a square, Oops, that wasn't very good. We draw across an X connecting our four corners. What we've done is we've found the center of that square. And through the center, we can draw a vertical and a horizontal line. And now we see the 4 points that our circle should connect with the square. And it shouldn't touch this square at any other point. And we can circumscribe this circle into the square and help make it a little easier to get a kind of nice round feeling. And we can do the same thing with an ellipse, but instead of a square, we're using a box, where I can draw my X that I didn't do very good, and find my ellipse inside of that box. So that's very useful for getting this kind of shape here, but actually that's not really what an ellipse is going to look like. Because in the same way that a square, when we say it back into space, doesn't just get shorter, its back compresses. The same thing happens to an ellipse. And so actually what we want to do is construct our ellipse in a square that we've constructed with a vanishing point. This way, when we find that middle point, you can see that the back side of our rectangle is shorter than the front side. That's what we want. And now I can go through and draw what will end up being a pretty good looking ellipse. And this is also very nice because, again, any set of parallel lines is going to seed to a point. So I can use this to find how curved, for example, the top and the bottom of a cylinder should be. And if that's a little confusing, just remember that just the same way that a box will, a plane would seem like just a flat line at the horizon, and then as it raised up, it would get more and more open. We would see more and more of that bottom, and the same thing going down, that more and more of the top of an object is going to get revealed as it goes beneath our eye level. The same thing is going to happen with an ellipse. We're very close to the horizon. An ellipse will seem almost like just a little sliver, and it will continue to get more and more open as it goes above and beneath our eye level. And constructing a cylinder in perspective can help us get that proper sense that, now that I erase some of my construction lines, is maybe a little more visible, that the curves at the top and bottom of the ellipse are properly extreme for how high and low they are above our eye level. So for right now, I think we'll call it with that. This is turning into a relatively lengthy video. We're going to continue talking about perspective, and in particular continue talking about the application of perspective to draw ellipses. But for right now, if you've been drawing along, this should get us on good footing. If you have any questions, please email me, drop me a message through Canvas, ask me in class. Otherwise, watch the other video, which will describe the homework in a little more depth. And I will see you in class.